Hey guys, today we're going to be talking about how to translate from other types of CVPM representations, not starting with the position time graph. And so to do that, we'll look at a couple examples. But before we do that, I want to go over the formulas for constant velocity. The first one is when we're looking at speed. Speed is distance divided by time. One thing to note about that formula is that it is only positive. It's always positive, and the distance, that's because the distance can only be a positive number, and so speed will always be positive while velocity can be negative. The next formula is the formula for displacement. To find the displacement of some object, you take its final position minus its initial position. If you know the final and the initial, you can figure out the change in position, also known as displacement. The next formula is the generic mathematical model formula that we use for our constant velocity representations. Okay, and it says position is equal to the velocity multiplied by time plus your initial position. This next one, it comes from the position time graph. Okay, it is the formula for velocity. The velocity is the slope of a position time graph, and slope is final minus initial position divided by final minus initial time. So if you use the xt graph, you'll be using this formula to calculate your velocity. Over here on this other one, this will be used whenever we're looking at VT graphs, and we're going to get an example later on. Whenever you have the velocity and the time, if you take the velocity multiplied by a change in time, that will give you the displacement of an object. So you're actually using a VT graph, you're actually able to go and figure out what the change in time is, or the displacement is. So again, the constant velocity particle model is when we treat an object like as if it were a single particle moving at a constant velocity. There are many representations that can be used. We have xt graphs, VT graphs, the mathematical model, motion maps, and word descriptions. Okay, so one of our examples is what happens if we take a motion map and turn it into a position time graph and figure out the other information. So the first step would be to go through and number our scale. And so for me, I'm going to say this is, looking at the horizontal axis, or the positions, we're going to go 0, 10, 20, 30, 40, 50. So now we have all of our data will fit on there. The next thing is to figure out how many seconds it is. And so it looks like our scale, or our dots are counting by 2 seconds. So I got 0, 2, 4, 6, 8, 10, 12, 14, 16 seconds. So I'm going to plug in the time. I believe I can fit it all on here. 2, 4, 6, 8, 10, 12, 14, and 16. The next step is to take those dots and place them where they go. So the first one is at 0 and 50. So I got a dot right there. The next one is 2 seconds later, we're at 30. So we place a dot there. Then we're at 10. We place another dot. Then it stays at 10 for a couple seconds before it goes and starts to increase each second. And then at the last one, it makes a big jump back to the end. Okay, and so that's the data that we have. And now I can go ahead and draw in my lines. And there's two ways I can figure out the, I can figure out the velocities. One is to use the velocity formula. Another method of figuring out the velocities would be to go and look at this motion map and know that, hey, this first section, I traveled backwards 20 meters, negative 20, over 2 seconds. So that velocity is negative 10 meters per second. Then we got a velocity of 0. Over here, this is going forward 10 over 2 seconds, which is going to be 5 meters per second. And the last section, I went from 40 to 10 That's negative 30. So I drop negative 30 over 2, which gives me negative 15 meters per second. Okay, so I got negative 10, positive 5, and negative 15. So I didn't have this labeled, but I know I have to be able to fit all of my information on there. So if I scale it by 5s on these dots, I can now plug in. For the first 4 seconds, we had a constant negative velocity of negative 10. I like to shade these in. And by shade in, I mean draw the arrow lines, go all the way up to wherever 0 is. Okay, and then for the next couple of seconds, we had no velocity. It was at rest. After that, we were traveling at 5 meters per second for 6 seconds. And then we had a final velocity section, negative 15. My equations: x equals negative 10 meters per second every second times the time plus initially we were at 50 meters. That was the equation that explains what's going on from 0 seconds till the moment in time of 4 seconds. Next up, x equals 0 meters per second times time plus 10 meters. That's when it stopped, and that was from 4 seconds to 8 seconds. Next up, x equals 5 meters per second times the time plus 10 meters. That was from 8 seconds all the way up to 14 seconds. And the last one, x equals negative 15 meters per second times time, plus that section started at 40 meters. And that would be from 14 seconds, which is less than, all the way up to 16 seconds. So whenever t was in that range, that was the equation that made sense.